Hi, in this video I am going to discuss Edexcel IAL January 2022 Unit 1 paper WPH 1101 paper. Okay, so Edexcel IAL January 2022 Unit 1 paper WPH 1101 paper. This is the first question. A student walks for 6 seconds. The displacement time graph for the student is shown, right? The displacement time graph for the student is shown. He is walking on a floor, right? Which row of the table shows the final displacement and the velocity of the student? So you can see in this graph, the displacement time graph, the displacement is starting from negative side, then finally the displacement is positive 2. Okay, if I show a block diagram, so this is the student. So imagine this is the student, he is walking. Initially displacement is negative 1 meters. That means maybe this is the reference point. So this is the reference point. Reference point is the point about which displacement is measured. You know, displacement is a vector quantity. We can measure the displacement from any point. If we want, we can measure the displacement from the initial point where the t equals 0. Or we can take any other point about which we can measure the displacement. So if I take, this is the reference point, and if I take towards right is positive. So initially the position of the student or the displacement of the student is towards left 1 meters. So that will be negative because it's opposite to the direction of I take. So he is walking this direction. He is walking towards positive because you know the gradient of the displacement time graph gives the velocity. Gradient of the displacement time graph gives the velocity. You can see the gradient, the slope is positive. That means the velocity is along the direction where I take it as positive quantity. So he is moving towards right where I took it as positive. So finally the displacement is plus 2 means from the reference point finally. So this is at time t equals 0. Then at time t equals 6 seconds, he is here. The student has come to this position, which is from the reference point, which is 2 meters. Which is 2 meters. So what is the displacement of the student? Always the displacement is measured from the reference point. So final displacement from the reference point, that is 2. Because the displacement is initially minus 1 means from the reference point it's towards left 1 meter, which is negative. So finally the displacement from the reference point, which I marked as O, towards positive side 2. The displacement is measured from the reference point. If we want, we can take reference point as the initial point, but in this question reference point is some other point, not the initial point where the student is starting the measurement. So the final displacement is from the reference point 2 meters, right? So the answer, displacement is 2 meters, which is positive quantity. The velocity, find the gradient of the slope. So velocity is the gradient. If I find the velocity, that's a gradient, that will be equal to 2 minus 0, the gradient, over 6 minus 2, that is going to be 2 over 4, that is 0.5 meter per second. That is a positive quantity towards right. So the answer is A. Displacement 2, velocity 0.5 meters. For the first question, answer is A. Already I did a complete video for the graphs, which includes displacement time graph, velocity time graph, acceleration time graphs, everything. Complete videos I did already too. So I'll give those who want to learn that, you can go through it. I'll give the link for those videos in my description of this video. So you go to the description part of this video. There I will give you the link for my explanation. Separately I already done it for graphs. That includes all type of graphs and the conversion of graphs, right? So you can go through it if you want additional information. Okay, question number 2. Physical quantities may be vectors or scalars. Which row of the table is correct? So you know that, force is a vector, Mass is a scalar, acceleration is a vector. You know that, even IGCSE you would have learned that. So the correct answer for question number 2 is D. Question number 2, the correct answer is D. Okay, question number 3, again it's based on graph, that is velocity time graph is given like this. The velocity time graph for a particle is shown. Which of the following is a displacement time graph for this particle? So you can see the velocity is decreasing, becoming 0 at particular time, then increasing in opposite direction. So it's something like, example I can say, if you throw a ball vertically upwards from a ground, the velocity in upward direction will decrease uniformly. It will decelerate at g, that is 9.81 meter per second square. It will reach the highest point where the velocity will become equal to 0. Then it will accelerate downwards. So the acceleration is downwards again, which is 9.81 meter per second square, until it hits the ground. So throughout the motion, the acceleration is constant. So you know, the acceleration is constant means, for example, if you throw a ball vertically upwards, the acceleration is downward direction, that is 9.81 meter per second squared. The ball will move upwards. So that means an object is accelerating or decelerating. How we decide it? If the direction of velocity is opposite to the direction of acceleration, the object will decelerate. If the direction of velocity is along the direction of acceleration, the object will accelerate. That means its velocity will gradually increase. If the acceleration and the velocities are opposite to each other, then the velocity will decrease. That means it will decelerate. So in this situation, if you throw a ball like this, it will move vertically upwards. The direction of acceleration is downwards. You can't change the gravitational acceleration. So if the resultant force is always fixed downwards, that's the weight, and it's not changing, the motion is opposite to the direction of the force, it will decelerate. So it will reach a point where the velocity will become equal to 0. Then the ball will fall down. When it falls down also, the acceleration is the same, which is naturally downwards. So it will accelerate again with the same magnitude. So that's the reason throughout the motion, the slope, the gradient is constant. Okay, I already explained all these things in my separate 2 videos related to graphs. I told that the link for those 2 graphs related to velocity time graph, displacement time graph, distance time graph, everything I discussed. So the link is given in the description part. Those who like, you can go through it. The full explanations are given there. Okay, so here we need to draw displacement time graph. So here they are not taking which is the reference point. If they don't tell which is the reference point when we are sketching or plotting a displacement time graph, we should take the initial point from where the ball is thrown, or the initial point will be the reference point. So in this example, I will take this point as a reference point. So if this is the reference point, what will happen? The initial displacement is equal to 0. So here the velocity initially shown by a positive quantity. So I can take the upward direction positive. So if I draw a displacement time graph here, so if I draw a displacement time graph for this motion, for this velocity time graph, initially the displacement equal to 0, because we should take the initial point as the reference point. The graph will start from 0. When the object moves up from the reference point, the displacement is increasing. So if the displacement is increasing in the positive side, my graph also should increase. At the same time, when you are drawing a displacement time graph, you should think about the gradient. Should I draw displacement time graph straight line or curve? Right. How we decide it? You know, the gradient of the graph that you are going to draw gives the velocity. So here the velocity is decreasing, the object is decelerating. You can see the velocity is decreasing, the object is decelerating to 0. That means the gradient of the displacement time graph I am going to draw should decrease. So gradient decreases means the slope must be like this. So the gradient of the graph should decrease. So where the gradient becomes almost 0, that means the graph should become almost horizontal, where if I draw a tangent, that must be 0. where the object is at rest. If I say this time t1, this should be the time t1. Right, now what's happening? From the reference point, I took this as the reference point from where I am measuring the displacement. The object has gone to the highest point, then it's coming down. So from the reference point, the displacement is decreasing. But when it comes down, you can see the velocity is increasing, which is negative side. The velocity is on the negative side. Why? When it falls down, the velocity will be downwards. The velocity will be downwards, which is opposite to my sign. I took upward direction positive. Why I took upward direction positive? Initial velocity is positive, which is upward. So when it falls down, the velocity is negative but increasing. So velocity is increasing means the gradient of my graph should increase, but the displacement from the reference point should decrease. So the graph should have an increasing gradient, but the graph should decrease. So the graph should be like this. So if the object is hitting the ground, the displacement went up should be same as the displacement is coming down. Finally, it will touch the ground. Finally, the displacement will be equal to 0 when the object comes back to the starting point. But here the question is not saying whether it's coming back to the starting point, but we know the shape of the graph increasing. Graph is increasing, slope is decreasing, then graph is decreasing, the displacement is decreasing where the slope is increasing. Only one graph like that. So the correct answer A. Question number 3, correct answer A. I'll give the link for those 2 videos related to graphs. You can go through it. I have done already these type of questions there. Okay, question number 4. This diagram is given. The diagram shows a student during a parachute jump on a windy day. The vertical component of the velocity is 5 meters per second and the horizontal component of velocity is 8 meters per second. She descends at an angle of theta to the vertical. That means the resultant velocity of these 2 components, V, which makes an angle theta with the vertical. Okay, so magnitude of the velocity and the angle. So it's nothing. We can think about the vector diagram. So we are not going to draw according to scale. We are going to sketch 8 meters per second. So 5 meters per second from here. So the resultant is this way. That's the resultant velocity. This is the angle theta. So in this triangle, how do you find the V? Pythagoras theorem, square root of 8 squared plus 5 squared. And the angle theta, I can say tan theta equal to opposite over adjacent. So theta will be equal to tan inverse 8 over 5. So velocity, angle. So the correct answer is C. Correct answer for question number 4 is C. Okay, question number 5. So question number 5, they are saying an object on the moon falls a vertical distance of 0.32 meter from rest in a time of 0.63 seconds. Which of the following expressions give the acceleration due to gravity on the moon? So nothing, not a big thing. So object is released from rest. It falls through a distance of 0.32 meter and it takes a time of 0.63 seconds. So the question is acceleration. So I can use downwards. S equal ut plus half at squared. U is 0. Initially the object was released from rest. So U equals 0. So the S is 0.32 equals 0 plus half a t squared, 0.63 squared. So I need to get an expression. So A is going to be first multiply 0.32 into 2 or 2 into 0.32 divided by 0.63 squared. So the correct answer C. Question number 5, correct answer C. Okay, question number 6. The graph shows how terminal velocity varies with mass for small spheres of equal diameter. So same diameter, varies with mass. So, but different mass means a different density of spheres, right? Equal diameter falling through a viscous liquid. Which of the following describes the gradient of the graph for a liquid of greater velocity? Okay, so uh, the terminal velocity means where the resultant force acting on the object becomes equal to 0. So when a sphere falls through a fluid or liquid, the three forces are acting on it. One is its weight, the upthrust, and the drag force. So the drag force is given by 6 pi eta r v. Upthrust is given by, you know that upthrust is given by volume of the object or volume of the displaced fluid, but object is completely inside the liquid, so volume of the object I can say, so because it's completely inside the liquid, so volume of the object into density of the liquid into G. So here volume of the object is 4 by 3 pi r cube, and they are using the same radius or same diameter, means upthrust will be the same for all spheres. Even when the weight of the sphere or mass of the sphere changes, they are changing the mass, but same diameter means upthrust will be the same for all objects, right? All the spheres, same upthrust. So at terminal velocity, the resultant force must be equal to 0, means I can say the resultant force up, if I take downwards, which is going to be 0, that is weight minus upthrust minus drag force. That must be equal to 0. That means I can say this, I can write the upthrust plus, when I take this to the right, this also to the right, upthrust is equal to upthrust plus the drag force 6 pi eta r vt. Vt is the terminal velocity, must be equal to mg. Is it? I took these two to the right, then I wrote it that those two on the left side. So u plus 6 pi eta rv equal to mg, right? At terminal speed, that means the forces are balanced. So I need to plot a graph of terminal velocity against mass. So I should make Vt subject, means I'll derive the whole equation. I'll divide the whole equation by 6 pi eta r. So that means u over 6 pi eta r plus Vt equal mg over 6 pi eta r. So I need to plot a graph of terminal speed, that should be the subject. So Vt equal to, then the mass on the x-axis, so that means g over 6 pi, I am writing this part, g over 6 pi eta r m minus, bring to the right, u over 6 pi eta r. Okay, so this is going to be like this. This is the y-axis. This is going to be the gradient, because all constant, g is constant, eta is constant, r is constant. So this is going to be the gradient. This will be the x-axis minus, this is going to be the intercept point. So here they are not telling this is origin, not marked on the graph. So this graph is not starting from the origin. So it's a straight line graph, y equal mx minus c graph. So the gradient is g over 6 pi eta r. So the gradient m is equal to, you can see g over 6 pi eta r. The question is, which of the following describes the gradient of the graph for a liquid of greater velocity? That means greater viscosity. That means if the eta becomes larger, the viscosity becomes larger, you know it's a denominator, so gradient will decrease. So gradient will decrease, or smaller gradient. Correct answer B. Question number 6. Correct answer B. Okay, question number 7. A person is pushing a trolley at a constant velocity. The flow exerts a force P on the person. Yeah, because person is pushing the flow backwards. So, according to Newton's third law, flow will push the person forward P. Anyway, they are saying it. They didn't describe it. I just told that. Force is exert force P. Sorry, flow is exert force P on the person. The person exerts a force Q on the trolley. The trolley exerts a force R on the person. and the total drag force on the trolley is S. So many forces are given, but they all are acting on different objects. Here two objects in three things: ground, trolley, the person, right? Which pair of the forces is a Newton's third law pair, P and R? So P is the force exerted, flow exerts a force P on the person, means its third law pair will be flow exerts a force P on the person. So person will exert a force P on the flow. They will be the third law pairs. There's nothing like that. Okay, when you think about Q and R, you can see the person exerts a force Q on the trolley. The trolley exerts a force R on the person. So you know, when object A exerts force on object B, the object B will exert the same magnitude of force on A. So that's a Newton's third law pair of forces. So here we know that Q and R are the third law pair of forces. So question number 7, the correct answer B. So Q and S, they are saying about Q and S. So obviously we know that S is a force which is it's a resultant force. So that won't have the drag force on the trolley. So the drag force on the trolley may be due to the friction on the wheels or whatever it is. So third law pair will act on the part where it exerting friction on the trolley. So that's not the answer anyway. But answer for question number 7 is B. Okay, question number 8. A wire breaks when a tensile force T is applied. A second wire made of the same material has twice the diameter. So that means area of cross section becomes 4 times, is it? Diameter becomes double. You know, area of cross section is given by 4 pi r squared. Diameter becomes double, means radius will become double. So the area of cross section becomes 4 times. Which of the following is the force required to break the second wire? Okay, so first you must know what is the breaking stress or ultimate tensile strength, means the maximum stress at which a material break. So careful, remember that the breaking stress or ultimate tensile strength, both are the same, depends only on the type of material. So breaking stress is defined as, breaking stress is defined as the force required to break it. I can call breaking force over area of cross section over area of cross section. Breaking stress is constant for a given type of material. For a given type of material, breaking stress is constant. So that means it is constant for a particular type of material. Breaking stress does not depend on the length. It depends on the, even it does not depend on the area of cross section. For a given type of material, it is constant. It differs for different type of material, but for a given type of material, breaking stress is constant, and it does not depend on the length or even area of cross section. Why do you remember area? It does not depend on area of cross section means when the area of cross section becomes double, the required breaking force will become double. So actually the area of cross section, when it varies for a given type of material, the breaking force also will vary, but the ratio will remain constant. I hope you understood that. So in this question, what's happening initially, so the breaking stress I can call sigma B. Breaking stress is T over A, area of cross section. The question is, which of the following force required to break the second wire? Second wire has double the diameter, means area of cross section becomes 4 times. For that also the breaking stress is the same. Same material, same breaking stress. The required force I can say T1 over area of cross section now 4 times, because diameter becomes 4, so 4A. So T1 is equal to cross multiply 4A over A, 4T. So the required tensile force is going to be 4 times of the earlier. So correct answer A, the first answer A. Okay, question number 9. A beam is balanced on two supports as shown. The beam has a weight W and the reaction force at the two supports are P and Q. The diagram is given. Which of the following statements about the magnitude of the force is correct? So you know that here this distance is smaller according to the diagram. If I say this distance Y, this distance X, if I name it. So if I take moment about the point where the weight is acting, you know it's at rest means the clockwise moment must be equal to anti-clockwise moment. So P into X that provides anti-clockwise moment, clockwise moment must be equal to Q into Y. If I take moment about the center of mass, which I can denote capital G. If I take the moment about center of mass, so I can say P into X, which provides a clockwise moment, Q into Y, which provides anti-clockwise moment. They must be the same. So I know that here, according to the diagram, Y is smaller than X. You can see the diagram Y, this length, the distance of Q from the center of mass where the weight is acting, Y is less than X. So Y is less than X means, you know, O-level max, Q should be greater than P. Q must be greater than P. Answer C. Question number 9. Answer C. Question number 10. Which row of the table contains two units that are not equivalent? Okay, joule per second, that means energy per time is watts. So unit 2 watts, so they are the same. We want to find those are not the same, right? So answer A, both sides are similar units, so that's not the answer. Second one, kilogram meter per second squared. You know, if you think about the unit Newton's second law, F equal ma, kilogram, which is mass, meter per second squared acceleration. So kilogram meter per second squared is Newton. Kilogram meter per second squared is Newton. On the right side, Newton is multiplied by second. So Newton cannot be same as Newton second. Certainly, is it? So those are two different units. So question number 10, correct answer B. Okay, now section B, question number 11. A slow-moving asteroid A was hit by a fast asteroid B. Asteroid B was absorbed by A as shown, so they entangled together. A part, state the principle of conservation of linear momentum. You can find it even in IGCSE books. So when there are no external forces such as friction, initial total momentum is equal to final total momentum. Or we can say when there are no external force such as friction, the total momentum before collision is equal to total momentum after collision. All of you know that, so I am not writing that answer. B part, before the collision, asteroid A had a velocity of 2.19 10 to the power 3 meter per second and momentum of 1.80 10 to the power 17 kilogram meter per second. Show that the mass of asteroid A was about 8.2 10 to the power 13. So nothing actually. This is okay, simple IGCSE type question. So B part, first part. So you know that momentum of A, moment is denoted by P, momentum of A is equal to mass of A into velocity of A. So momentum of A is given 1.80 10 to the power 17 equal to mass of A, we need to find it. Velocity of A before collision is given as 2.19 10 to the power 3 meter per second. So from it, mass of A which is constant before or after collision, mass of A will be 8.22 10 to the power 13 kilograms. So they asked to show it's approximately equal to 8.2. So 8.2 10 to the power 13 kilogram. Okay. Second part, calculate the velocity of the asteroids after the collision. Mass of B is given. Velocity of asteroid B before the collision also given 1.50 10 to the power 3 meter per second. Okay, so second part we can use law of conservation of momentum. So I'll use it towards right because both velocities are towards right before collision. After collision also they are moving towards right. Okay, so the velocity, the initial total momentum of asteroid A already given 1.80, that's given here 1.80 10 to the power 17. Velocity of momentum of B, I need to find it. So mass of B is given 5.90 10 to the power 12. The mass of B into its velocity before collision, 15 into 10 to the power 3. Now they have entangled together, so both will move with the same velocity. So I can add their masses because if they become one object, so the 8.22, that's the mass of A, 10 to the power 13, plus mass of B, 5.90, 10 to the power 12 into V. I need to find the velocity after collision. So solve it. You will get 3047.7 meter per second. So that I can write 3.048 into 10 to the power 3 meter per second. Okay, question number 12. The diagram is given. The diagram shows a lift system for moving people up and down a tall building. There is a counterweight to balance the weight of the lift. An electric motor is used to raise and lower the lift. Okay, so the A part, explain how the counterweight affects the amount of work required for the electric motor to raise the lift. So actually the lift, this is the lift where the people are there, this is the counterweight. So this is the electric motor passing like a wire or chain passing over a motor, electric motor with a pulley. Right, so what happens? So what will be the work done? Say for example, when it's moving at constant velocity, so if the lift moves up at constant velocity, the lift is gaining gravitational potential energy. So gaining gravitational potential energy is due to both work done by the motor and loss in gravitational potential energy by the counterweight. So actually we can say here, when the lift moves up, the counterweight will go down, is it? So when the counterweight moves down, it's losing gravitational potential energy. Because of losing gravitational potential energy, the counterweight also doing work on the lift. So because of losing gravitational potential energy, the counterweight also doing work on the weight to lift it up. So the total gain in GPE or the total work done on the lift to raise it to a height, that is due to that will be the outcome will be gain in GPE of the lift is equal to both work done by the counterweight because of losing its GPE plus work done by the motor. So the work done by the motor will be less because of part of the required work done to raise the lift is done by the counterweight. Okay, question number 12, big part. The electric motor raises the lift through a height of 40 meter in a time of 30 seconds. Show that the output power of the electric motor is about 12 kilowatts. Total mass of lift and people 2250 kilogram. Mass of counterweight is 1300 kilograms. So the same equation what I wrote earlier. So actually I already told that the counterweight is doing work because of loss in GP of the counterweight, is it? Counterweight is moving down, so it's losing GP. So here we assume they are moving down, the counterweight is moving down at constant velocity, lift is moving at constant velocity upward direction. So no change in kinetic energy, right? So here we need to find first, they ask you to find the work output power of the electric motor. Means first we should find the work done by the electric motor. So already I wrote the equation. So again I can say work done by the electric. So actually here they are saying the work done by the motor is equal to gain in G. Sorry, work done by the electric motor plus loss in GPE of the counterweight equal to gain in GPE of the lift. So gain in GP is the work done on the lift. Work done on the lift means gain in GP. Remember that work done on the lift means gain in GPE. So gain in GPE of the lift equal work done by the motor plus work done by the counterweight means loss in GP of counterweight. Okay, work gain in GP of the lift is the work done on the lift. So lift is moving up through 40 meters. Total mass of the people given. So mgh. So mass of the lift is 2250. M into G 9.81 into 40 equal to work done by the electric motor. I need to find it. Let it be W plus loss in GP of the counterweight is the work done by the counterweight. So that is mass of the counterweight is given 1300 kilogram. Mg is 9.81. So when the lift moves up through 40 meter, counterweight will move down through 40 meter. So from this find the W. So W will be equal to 37,2780 joules. That's the work done by the motor. So output power of the motor. So power of the motor. So this is the work done by the motor means power output of the motor. So this is the work done by the motor. Power output means work done over time. So 372780 divided by time is 30 seconds. Solve it. You will get 12,426 watts. So that is 12.43 kilowatts. So they have to show approximately 12 kilowatts. Okay, C part. The electric motor dissipates energy to the surroundings at a rate of 3600 watts. So the electric motor, you are giving input electrical energy, yeah, or electrical power per second. Energy per second is the power. So out of that, all the energy given as electrical energy will not be the useful output energy, because certain amount of energy will be lost to surrounding in the form of sound and heat. That is 3600 watts. So what is the total input energy? Total input energy in the form of electrical energy, or what is the total power, input power to the motor will be the useful output power, which is 12,426 plus the power wastage in the form of sound and heat, that is given as 3600 watts. So that will be the total input power. Useful output power is this much. So efficiency is the question. So I'll do the C part here. Efficiency equal total input power in the form of electrical power is this one, 12,426 watts plus the power wastage, which is 3600 watts. Useful output power is 12,426 into 100%. So the final answer will be 77.5%. Okay, question 13. The Tyrrell traverse in a technique for crossing a deep valley. The photograph shows the climber crossing a river using this technique. The climber moves along a rope suspended from the bank on either side of the river. So there's a photograph. We don't need that here. A part, the free body force diagram for the climber is shown below. The weight of the climber is 650 Newton. Show that the tension in the rope. Okay, so A part, the diagram is given, the free body force diagram. So this is 650 Newton, these two tensions on either side, same on the same string. So these angles are given 76 degree, this also 76 degree. So since is at equilibrium in vertical direction, the resultant force must be 0, resolve it vertically. T cos 76 plus T, this resolve it vertically, cos 76 minus 650 must be equal to 0. That is 2t cos 76 equal 650. Find the t. That will be 1.3. Sorry, 1343 Newton. So they have to show that about 1.3 10 to the power 3 Newton. Okay, B part, a diagram is given. The string is suspended between two supports. So the length has increased. So the initial length of the string is given as 120 meters. And the force acting on is same as 650 Newton. The question is, the rope has an unstretched length of 120 meter as shown below. Determine the strain in the rope while it is supporting the weight of a climber. You may ignore the weight of the rope. Okay, so I need to find the actual length because they ask you to find the strain on the rope. You know, strain is equal to extension of original length. So actually, you know, this is the initial length of the rope, which is 120 meters. So this total length will be more than 120 meters. I need to find the total length of the rope. How can I find it? So I can say now the total length to find this one side of the length, let it be x. Let this one side as x, so this also x. So this length in this this triangle, so if I consider this right angle triangle, this angle is 76 degree, this also 76 degree. So I'll find the length x. So x plus x, 2x will be the total length after tension is acting on it. Initial length is 120, I can find the extension is 6. So I'll find the x. So the total length is 120, the weight is acting at the center, which is 650 Newton. So this length I can find, this length is 60 meters. The total length is 120. This is acting at the center. So this will be 60 meters. So I can say sine 76 equal to 60 over x. In this triangle, if I consider this right angle, this is 90 degree. In this right angle triangle, sine 76 is equal to opposite, that is 60, half of 120 divided by x. So from that I can find x is equal to 61.84. So the length of the rope are under tension. So I can say length of the rope under tension equal 2x, x plus x, 2x. So 2 times 61.84, 2 times 61.84 meters. So that will be, I can find it that will be 123.68. So extension delta x, extension is equal to total length currently 223.68 minus 120. So that's going to be 3.68 meters. That's the extension. They asked to find the strain. Strain is equal to extension over original length given on the data sheet. So 3.68 over initial length 120. So that will be 0.031. That has no unit. So this is the B part, first part. What we did is the B part, first part, we already answered it. Now B part, second part, I'll do it here. B part, second part. B part, second part. The question is, the rope has cross-sectional area of 3.14 10 to the power minus 4 meters square. Determine the Young modulus. You know Young modulus is equal to tensile stress over tensile strain. So we already found the tensile strain, 0.031. We already found it. So we need to find the tensile stress. So tensile stress is equal to tensile force. I will put T, tensile force over area of cross section. Tensile force we found it in the A part, which is 1343 Newton divided by area of cross section given, which is 3.14 10 to the power minus 4 meters squared. So that's going to be 4.28 10 to the power 6 Newton per meter squared. So Young modulus is equal to tensile stress over tensile strain. Tensile stress 4.28 10 to the power 6 divided by strain, we found it 0.031. So that will be 1.38 10 to the power 8 Newton meter squared is the unit of stress. Strain has no unit. So the final answer, Young modulus, also same as the unit of the stress, which is Newton per meter squared, or you can give it in Pascal. Okay, question 14. This diagram is given. A student of weight 600 Newton is standing on a weighing scales in a lift. The scales are calibrated to give readings in newtons. The lift moves upwards at constant velocity, then decelerates to rest. As the lift moves, the student looks at the readings on the scales. Explain the readings on the scale. Okay, right. So normally students think the weighing scale reads the weight of the object. No, it always reads, a weighing scale always reads the push by the person, or the third law pair of the normal reaction. We'll think about the free body force diagram first. So imagine there's a weighing scale. This is the weighing scale. So on this weighing scale, an object is kept on it. So the weighing scale may be kept on a floor, whatever it is. Right. So if I draw the free body force diagram, we can see which force is it going to read. The weighing scale, which force is it going to read? Okay, if I draw the free body force diagram for the object. So first I'll draw the object. Then I'll think about the weighing scale separately. I'm going to show the relevant forces. Okay, the object has weight. The weight of the object will act downwards. So the weight of the object will act downwards. That is due to pull by earth. Earth is pulling the object down. So object will pull the earth up. So in case if I want to draw the third law pair of this force, I should draw it on earth. This is the earth. On earth, I should give the same force upwards. I can say pull by object. How much is it? That will be equal to same as mg. So earth is pulling the object down. According to Newton's third law, object will pull the earth up. We all are pulled down due to our weight. So earth is pulling our body down. So we all are pulling the earth upward direction. Okay, so this is the third law pair of it. We don't need this diagram in this question. I just drew it. Okay, now if this is the only force acting on the object, you know there is no force to balance this, the object would have fallen down. But object is not falling down. What's happening? The object is trying to fall, so it will push the weighing scale. It's kept on the weighing scale. This is the weighing scale. So object is kept on the weighing scale. So object will try to fall down and it will push the object down. I can say push by object. Push by object. How much is it? We'll see that. Object is pushing the weighing scale down. So when the object pushes the weighing scale down, according to Newton's third law, weighing scale will push the object upward direction. Push by weighing scale. Okay, so we normally have a special name for this type of forces, push by object or push by ground. We call it as normal reaction and we denote it as capital R. So if the magnitude of this force is capital R, this magnitude also same because they are Newton's third law pair of forces. So now only two forces are acting on the object. Now you can see which force is it going to read. Now if you keep a weighing scale on a table and you push it by your finger, you can see the reading will increase. So which force is it reading? Is it reading your weight or is it reading the weight of your finger? No, it reads the push you are giving it. Okay, so when you keep a weighing scale on a table and just push by finger, you will see the reading of the weighing scale will increase. Or if you keep a weighing scale on a table and keep a fan above it, due to the push by the air particles, the fan, the reading will increase. You can notice that, right? So that means the weighing scale reads whatever the force acting on its pan or on top of it. So the weighing scale is going to read this value. Push by the object will be read by the weighing scale. That means the weighing scale reads the third pair of this one because these two are same magnitude. That means I can say weighing scale reads the third law pair of the normal reaction. We have a special name, I already told that. Push by the weighing scale or push by the table we call normal reaction. So I can say these two are third law pair of forces. So I can say weighing scale reads the third law pair of the normal reaction, not the weight. Okay, now we'll think about different situations. If the object is at rest, the forces must be balanced. So here we can consider different situation. First situation, if the object is at rest, or the system is at rest, weighing scale is at rest, object also at rest, everything is at rest. So the resultant force must be equal to 0. So I can say R minus mg. The forces acting on the object are 2. They must be balanced. So R is equal to mg. So there the R, the numerical value of the normal reaction equal to weight of the object. So this reads the third law pair of this one. These two are having the same magnitude. So the reading will be equal to mg. Or I can say the magnitude of the reading is equal to weight of the object. So careful, don't say the weighing scale reads the weight of the object. Normally IGCSE, we also tell the students that weighing scale reads the weight. But actually it never reads the weight, it reads the push by the object. The push by the object can have a numerical value equal to weight of the object only when the object is at equilibrium where the resultant force is equal to 0. Okay, so second situation I can think. Imagine the object is kept inside the weighing scale and the object everything together kept on the surface or flow of a lift, and lift is accelerating upwards. So if the lift is accelerating upwards, say for example when you are standing inside a lift and when the lift accelerates, your body should have the same acceleration as the lift. If your body has low acceleration than the lift, what will happen? Every moment the velocity of your body will become smaller than velocity of the lift. That means the displacement of your body will become smaller than the displacement of the lift. So you have to break the lift and come out. That never happens. So when you are inside a lift and when the lift accelerates upwards, your body also will accelerate at the same magnitude. Same way when the object with the weighing scale kept on the flow of a lift, and when the lift accelerates upwards, the object also will have the same acceleration as the lift. So object is accelerating. What's the numerical value of the acceleration? That will be same as the acceleration of the lift. Let it be symbol A. So if the object is accelerating vertically upwards, same as the lift, the object must have a resultant force. According to Newton's second law, the object must have a resultant force. So these are the two forces acting on the object. So the resultant force acting on the object I can call F. That must be equal to R minus mg, because object is accelerating upwards. It should have a resultant force, but there are only two forces acting on it. So it should have a resultant force. This must be larger than this. The weight of the object never changes. R will change depending on the acceleration. You can see that equal to F equal ma, the mass of the object into acceleration of the object, that is same as the acceleration of the lift. Now make the R subject. R is equal to, bring it to the right, ma plus mg. So the numerical value of the normal reaction is not equal to weight, it's more than weight by ma. So the normal reaction has increased from weight. Earlier it was equal to weight, the object is at equilibrium. Now it is equal to ma plus mg. I already told that weighing scale reads the third law pair of this one. Now the reading will be equal to ma plus mg. That means the reading of the reading of the weighing scale will become greater than the numerical value of the reading of the weighing scale will become greater than the normal reaction, greater than the weight of the object. The numerical value of the reading will become greater than the weight of the object. Okay, third situation, the lift is decelerating. So the lift is decelerating means, same as earlier I explained, the object also should decelerate with the same magnitude. Otherwise what will happen? The velocity of the lift will slow down, but your velocity will be more than the velocity of the lift. So you will break the lift and come out. That never happens. So when the lift decelerates, your body also should decelerate when you are inside the lift. Same way, when the lift decelerates, the object also should have the same deceleration. So if the lift is decelerating upward direction means, I already explained, the velocity is upward, the lift is moving upwards, and decelerating upwards means acceleration is downward, opposite to the direction. So or we can say upward direction, it's decelerate. So the resultant force is equal to, if I say the upward force smaller than the downward force, so that becomes, I can say like this, it's decelerating upward direction means the acceleration is downwards, opposite the direction of velocity. I already told that when an object decelerates means the direction of acceleration is opposite to the direction of velocity. It's moving up and decelerating, so the acceleration should be downwards. So R should become smaller than mg. So F equal mg minus R equal to ma, or you can write upward direction, same thing, F equal R minus mg equal to m into minus a, because acceleration should be downwards because it's decelerating. Moving upward, acceleration should be opposite to the velocity, downwards, so it should be minus a. Either way you can write. So when you make the R subject here in any of these equations, if you make the R subject here or here, whatever it is, it will become mg minus ma. That means the normal reaction will become smaller than the weight. You are subtracting a quantity from the weight. So the reading of the weighing scale will become smaller than the weight of the object. Okay, so this is the explanation I can give related to reading of a weighing scale. So I explained everything already. So if the object is accelerating downwards, same way you can say a lift is actually moving down and accelerating down means there also you can do the same thing again with the same resultant forces, right? So remember that weighing scale always reads the third law pair of the normal reaction. Here the reading will be smaller than the weight of the object. Okay, question number 15. A hollow brass cylinder with closed ends is floating on the surface of water. The cylinder has a length of 4 centimeter and an external diameter 2.1 centimeter as shown. There's a diagram given. 63% of the volume of the cylinder is submerged. The cylinder contains negligible weight of air. Explain why the brass cylinder floats. Okay, why it floats? You know Archimedes Principle, the buoyancy effect. So if it is floats, we know that according to Archimedes Principle, upthrust is given by weight of the displaced fluid that will act upward direction, and the weight of the cylinder is only due to the material, the metal part of the cylinder, not the whole volume. You know, inside there is vacuum, or maybe inside there is air, its weight is negligible. So the weight of the cylinder is only due to the metal part of the cylinder. So why is it floating? The upthrust is equal to weight of the cylinder. We can say there are only two forces acting, upward, upthrust, and the weight downwards. Upthrust is the weight of the displaced water. So upthrust is equal to weight of the displaced water. That's the reason the cylinder is floating. Okay, so the B part, density of water is 1000 kilogram per meter cube. Show that the mass of the cylinder is about 9 into 10 to the power minus 3 kilogram. So we know that the upthrust is equal to volume of the displaced water. So we can see this B part, first part. So volume displaced . So volume of water displaced, sorry, I can write volume of water displaced equal to volume of cylinder inside water. So they are saying 63% of the volume of cylinder is submerged, and we can find the volume of the cylinder. We know the length, we know the diameter, so we can find the area of cross section, pi r squared. Everything should be converted to meter. So volume of the cylinder inside, we can say pi, the radius is 2.1, into 10 to the power minus 2 divided by 2 because that's a diameter pi r squared into the length 4 centimeter 4 into 10 to the power minus 2 into 63%, 63 over 100. So that much of meter cube pi r squared. So here that's with square, not clear, pi r squared, right. So when you solve it, it will become 8.73 10 to the power minus 6 meter cube. The question is, the density of water given, show that the mass of the cylinder. So we know that since it floats, already we showed it, mg equal to upthrust. What is upthrust? Weight of the displaced water. So upthrust is equal to volume. I can call this as V. Volume V, I'll call this as V, into density of water into G. That's the weight of the displaced water. That will be the upthrust. So I can say mg equal to volume. We found it 8.73 10 to the power minus 6 into rho W 1000 into G, because this G and this G will get cancelled. Find the weight of the cylinder. That will be 8.73 10 to the power minus 3 kilogram. So approximately we can say, which 8.73 as 9 into 10 to the power minus 3 kilogram. Okay, question 15, part B, second part. Deduce whether an identical hollow cylinder made of gold would also float. Assume that the volume of gold is same as the volume of brass. So actually they are not saying the volume of the cylinders are the same. They are not telling it. They are saying the volume of the material used in the cylinder where it's made of brass, and the volume of the cylinder made of gold where the volume of the gold, not the cylinder, the material part, right? They both have the same volume. They are saying it. So density of gold given 19.3 kilogram, 19.3 10 to the power 3 kilogram per meter cube, and density of brass is 8.7 10 to the power 3 kilogram. So you know we can find the mass of the cylinder made of gold. We can find it by using the volume. They are saying both are made of same volume. The materials are the same. The volume is the same for both gold and brass. We know that density is equal to mass over volume. So volume is equal to mass over density. So both volumes, the volume of the gold and the volume of the brass, are the same. So we know the mass of the brass. Earlier we found it, that is 8.73 10 to the power minus 3 kilograms. So 8.73 10 to the power minus 3 over density of brass is 8.7 10 to the power 3. That is for the brass, volume of the brass. That is same as volume of the gold. We need to find the volume of the, mass of the gold divided by the density of the gold, 19.3 10 to the power 3. So from this we will find the mass of the gold in the cylinder. That is going to be 19.4 10 to the power minus 3 kilogram. So we can find the weight of the gold cylinder equal mg. That is going to be 19.4 10 to the power minus 3 into 9.81. So that will be 0.19 Newton. So the question is, earlier when the cylinder of that particular dimension, 4 centimeter length, 2.1 centimeter diameter of cross-sectional surface, when it is made of brass, 63% of the cylinder sink inside the water, balance is outside the water, it was floating there. The question here, when the same size of cylinder is made of gold, here also the volume of the gold is same as the volume of the brass in the earlier cylinder. Will this cylinder which is made of gold float in water? So what percentage inside water, what percentage outside water is not? Will it be able to float in water? That's the question. Okay, so there we can find out like this. Okay, if it is floating, here also the weight of the gold we found it must be equal to upthrust of the given by the water. So if it want to be equal to upthrust is equal to weight, now we can find out what must be the volume of water to give out. So what volume of water should be displaced to balance this weight? We'll find it. So we can say if the cylinder floats, if the gold cylinder floats, then the upthrust must be equal to the weight of the cylinder, which is 0.19 Newton. So upthrust, the volume of water that must be displaced into density of water into G must be equal to 0.19 Newton. So I am going to find what volume of water must be displaced. Then we will check that volume of water that must be displaced in order to make the gold cylinder float. We'll check that volume with the volume of the cylinder. Right? So we'll find the volume of the water that must be displaced. So V into 1000 into 9.81 equals 0.19. Find the volume of water that must be displaced. So here V is the volume of water that must be displaced. So we can say where V is the volume of water that must be displaced. Okay, so when we find the volume of water that must be displaced, that becomes 1.94 10 to the power minus 5 meter cube. So we'll compare this volume with the volume of the cylinder, the earlier cylinder. What the diameter of the cylinder we know, length is 4 centimeter, the diameter of the cross sectional, the circular part is 2.1 centimeter. So we'll find the volume of the cylinder. We already found it earlier, but again I'll find it. Volume of the cylinder equal pi r squared h, pi into 2.1 10 to the power minus 2 divided by 2 all things squared into 4 into 10 to the power minus 2 meter cube. So that is going to be 8.73 10 to the power minus 6 meter cube. Sorry, not, yeah, I'll check that. Okay, that is 1.39 10 to the power minus 5 meter cube. Okay, so that is the volume of the gold cylinder according to the same dimension as the brass cylinder. So that's the volume of the gold cylinder 1.39 10 to the power minus 5 meter cube. But if the gold cylinder wants to float, the volume of water that must be displaced is 1.94 10 to the power minus 5. That means it should displace a volume of water which is more than the volume of the cylinder. That never happens. Even if the cylinder completely sink into water, the volume of water that could be displaced is equal to volume of the cylinder, which is 1.39 10 to the power minus 5 meter cube. So the required water to be displaced in order to float the cylinder is 1.94 10 to the power minus 5 meter cube. So this cylinder never floats inside water. So you should give that conclusion. So the volume of the water that should be displaced is larger than the volume of the cylinder. The required water will not be displaced in order to float the cylinder. So that means the volume of the cylinder has to be larger to get this required upthrust. Okay, question 16. The photograph shows a toy pinball machine. The launcher is pulled back, compressing the spring. So the diagram and everything are given. So when the launcher is pulled back, the spring is compressed by 5 centimeters. So the compression is 5 centimeter. When the spring is released, the ball is launched at a speed of 8 centimeter per second. Show that the kinetic energy of the ball after launching about is 4 into 10 to the power minus 5 joule. Mass of the ball is given. So just like IGCSE type question. So question 16, A part, kinetic energy equal half mu squared. So the mass is given 12 grams, 12 into 10 to the power minus 3, convert to kilogram. The speed is given 8 centimeter, convert to meter per second. So divide by 100, all things squared. So solve it, you will get a 3.84 10 to the power minus 5 joules. So approximately 4 into 10 to the power minus 5 joules. Second ball, determine the force on the ball when the spring is released. So the force on the ball, so we can use by using energy is given. We found it 3.84 10 to the power minus 5. So at the moment it is released, what's the force acting on it? So we can say energy E equal half F delta X. So use that one. We know the energy 3.84 10 to the power minus 5 half F, that's average force acting on it, delta X. The compression is given 5 centimeters. So when it is 5 meters, determine the force on the ball when the spring is released. So that's the initially. When you release, what's the force acting on it? You know the force will decrease later when the spring comes back to initial length. From the compression, when it comes back to initial length, you know the compression is going to decrease. Initially the compression is 5 centimeters. So when the spring expands or spring returns to original length, the amount of compression will decrease. So according to F equal K delta X, Hooke's law, the force will decrease gradually, right? So based on that, the last part graph is, they asked to draw the graph, D part. I'll explain again later. So anyway, they asked you to find the force when the spring is released. So that time the force is F and the compression is 5 centimeter. So we can write 5 into 10 to the power minus 2. So from this, find the F, that is 1.54 10 to the power minus 3 Newton. So C part, Determine the stiffness. So stiffness is the spring constant K. So C part, we know the force F equal K delta X, Hooke's law. So force 1.54 equal 10, into 10 to the power minus 3 equal K into delta X 5 centimeter, 5 into 10 to the power minus 2. So find the K, that will be equal to 0.031 Newton per meter. Okay, so deep part I told that. So deep part, they are asking the spring returns to its original length L. So it was compressed through 5 centimeter. So when it released from 5 centimeter compression, it's coming back to the natural length, which is capital L, right? Sketch a graph on the axis below. They are giving an axis, y-axis velocity. There's a y-axis velocity of the ball against length of the spring. So that is length of the spring. Okay, so sketch a graph on the axis below to show how the velocity of the ball varies with the length of the spring. Okay, so imagine, so this is the spring initially, L. So it's compressed by 5 centimeter, and imagine you are keeping a ball here. So this is 5 centimeter amount you compress is 5 centimeter. So when it's fixed, imagine this left side is fixed. Okay, when you release, the initial velocity of the ball is 0. So your graph should start from 0. So the velocity initially must be 0. Yes, I can put the initial velocity 0. Here this is given 0 on the diagram. So velocity, I'll put the initial velocity 0. So this initial length of the spring is, I can say L minus 5 centimeters. So length of the spring, they didn't give the unit. If you want, you can put it as centimeter. No problem. So I can say the initial length of the spring is L minus 5 because it's compressed by 5 centimeter. So initial length is 5. At that moment, the ball is released. The ball will be released with initial speed 0. So now what happens? The ball is accelerated. So the ball is going to accelerate from 0. What will happen to the acceleration? You know the force acting on the ball. If I think about the free body force diagram, weight downwards, there could be a normal reaction, whatever it is. So the acceleration of the ball is due to the force exerted by the spring, which is F equal K delta X. So initially the delta X is 5 centimeter, force will be the maximum. Then what's happening? Delta X, the amount of compression is decreasing from 5 centimeter, it will become 4 centimeter, 3 centimeter, 2 centimeter, like that. The amount of compression will decrease when the spring returns to its original length. So the force is going to decrease. So force is decreasing means there is acceleration. If I think about this is equal to ma, there is acceleration, so the acceleration will decrease. So the velocity is increasing, acceleration is decreasing with time. Acceleration is decreasing with time means the rate of increase of velocity will decrease with time. Rate of increase of velocity will decrease with time. There is increase in velocity, but rate of increase of velocity will decrease with time. So it decreases with time means it decreases with length of the spring. When the length of the spring increases, the rate of increase of velocity also will decrease, because when time passes, length of the spring is increasing, rate of increase of velocity will decrease. So what will happen? The graph should have a decreasing gradient. Finally, the velocity should become how much? We already said 8 centimeter per second. So initially it's starting from 0 velocity. The velocity will increase. Rate of increase of velocity will decrease with increasing length of spring, because the amount of compression is decreasing, acceleration is decreasing. So the graph will be having a decreasing gradient. So when the length becomes L, so L is marked here, when the length becomes L, the velocity will become 8 centimeter. So the graph must be this shape. A curve with decreasing gradient. a curve with decreasing gradient. Okay, question number 17. A small sphere is moving horizontally through a viscous liquid. Stokes' law can use to calculate the drag force on an object. A part. State the conditions that must be applied for Stokes' law to be valid. So you know there are two conditions. The object must be spherical shape. The second one, the fluid flow around the sphere must be laminar. All books says that, right? So that's the answer for A part, two conditions. B part, there's a constant force of 2.3 10 to the power minus 5 Newton acting horizontally on the sphere. Diameter of the sphere is given. Viscosity of liquid also given. At one instant, the speed of the sphere is 5.2 10 to the power minus 3 meter per second. Calculate the resultant force on the sphere. So it's moving horizontally through a liquid. Okay, so it's not normally we give questions. It came in the past paper. Sphere is falling down or sphere is released and moving up, but here it's moving horizontally. So we don't need to consider about the vertical resultant forces. We should assume there are no resultant vertical forces, only horizontal force we need to consider. So there's a sphere. So B part. There's a sphere. It has the horizontal constant force is acting. We don't know what force is it, but there's a constant horizontal force which is 2.3 10 to the power minus 5 Newton. So there will be a drag force, FD, drag force. We know that 6 pi eta RV, right? So we need to find the resultant force horizontally. So I can say resultant force F equal F1 minus FD, the drag force. So we know the F1, which is 2.3 10 to the power minus 5. The drag force we know 6 pi eta RV. Substitute the values, 2.3 10 to the power minus 5 minus 6 pi. The viscosity is given as 7.1 10 to the power minus 2 Pascal second. Radius is given as diameter given, so we have divide by 2, 4.5 centimeter, convert to meter, divide by 2, 10 to the power minus 3, sorry. Into V, the speed is given. We need to find the resultant force at that particular speed. So speed is 5.2 10 to the power minus 3. Solve it, you will get the resultant force, that is 7.31 10 to the power minus 6 Newton. That's the answer for B part, first part. B part, second part. Calculate the maximum speed of the sphere in the horizontal direction. Maximum speed is the terminal speed, is it? It can't increase beyond that. So terminal speed occurs when the forces acting on it in horizontal direction are the two forces. They balance each other. So second part you can say the maximum speed is the terminal speed where the resultant force is equal to 0. So maximum speed is the terminal speed. Where F equals 0, the resultant force must be equal to 0. So we know the constant force applied externally, which is 2.3 10 to the power minus 5. So Fd minus F1 equals 0. 6 pi eta R Vt minus 2.3 10 to the power minus 5 equal to 0. So we need to find the Vt. So 6 pi eta we know that given as 7.1 10 to the power minus 2. The radius we have to find it, 4.5 10 to the power minus 3 divided by 2. Vt I need to find it, terminal speed, equal to, bring it to the right, 2.3 10 to the power minus 5. Solve it and find Vt, the terminal speed. That will be equal to 7.64 10 to the power minus 3 meter per second. That's the maximum speed, that is the terminal speed. Okay, same question. Question number 17, part C. A larger diameter sphere in the same liquid is acted upon by the same constant force as in part B. The liquid is at lower temperature. So lower temperature means the coefficient of viscosity of the liquid will increase. Explain the effect these changes have on the maximum speed of this sphere. Maximum speed, I already used that idea, terminal speed, right? So I can say this is the sphere. It has a constant force which is acting towards right. I take it as right, which is already we know that constant force is given as 2.3 10 to the power minus 5, and there's a drag force which is given by 6 pi eta RV. Okay, terminal speed means this drag force must be equal to the constant force, or minus constant force minus 2.3 10 to the power minus 5 equal to 0. That means this must be equal to this one. So now what is happening? The same sphere, the larger sphere, they are using a larger diameter of sphere, means R is going to be larger, and the temperature of the liquid is lower, means viscosity is going to be larger. So they are going to use a larger diameter sphere with a lower temperature. So what will happen to the terminal speed? That's a question. Okay, we know that when the temperature decreases, coefficient of viscosity will increase. The radius also increasing. So simple mathematics. To balance this quantity with this quantity, where eta is increasing, R is increasing, what will happen to the P? P will become smaller. Very simple. But we have to give it in words. We can say when the temperature increases, coefficient of viscosity will increase. When the diameter increases, the radius also will increase. Therefore, to balance the same constant force with the drag force, what will happen? For the same velocity, at a particular velocity, the increase in for the increase in viscosity will increase the drag force. Therefore, at lower speed, it will reach the maximum speed. The lower speed, it will be able to balance this quantity. R is increasing, eta is increasing, means we will become smaller. That's a very simple mathematics, but we need to put it in words. So question 18 is the last question. It's on projectile motion. So already I did 2 complete lessons related to projectile motion. So the link for those 2 lessons also will be given in the description part of this video. So I did 2 different 2 different videos for the projectile motion. So the link or the URL for those lessons, projectile motions, also will be given at the description of this video. Also, I told that there are two separate videos for graphs that also will be given. So there will be 4 different links given in the description of this video, 2 for projectile motions and the other 2 links for 2 different videos related to graphs. If you like, you can watch them. So those videos are complete videos for both projectile motions and graphs, right? Okay, so here this is a simple question. So a motorcyclist is traveling and leaving at an angle 25 degree at a velocity of 35 meter per second at a height of 3 meters above a river. The width of the river, I marked it with blue coloring. So the width of the river is 100 meters. So he wants to cross this river. So will he land on the other side of the bank of the river? So 100 meters, or will he fall into water? So simple thing, we need to find the range of the motorcyclist for this particular velocity at this angle. So simple question. Anyway, they are asking part by part. A part, they ask you to find the both horizontal and vertical velocities, initial velocities. So I can say initial vertical velocity, that is 35 sine 25. So that will be equal to 14.8 meter per second. Initial horizontal velocity, that is 35 cos 25, that will be equal to 31.7 meter per second. Okay, next part, that is B part. Deduce whether rider lands on the other side of the river. The effect of air resistance can be ignored. Okay, so the B part, I need to find the range of the projectile. Here the projectile is the motorcycle. So we need to find the range of the projectile for this particular velocity at a height of 3 meters. So we'll need to find the time taken. So if he wants to land here, if he wants to land on the other side, he should move down 3 meters. He should have a vertical displacement of 3 meters. So there's a chance he can jump like this and land on the other side, or he can jump from here and land inside water. So if he is landing on water or landing on the other side, his vertical displacement is 3 meters downwards. So we'll find the time taken to have a vertical displacement 3 meters downwards. We'll find the time for that. Then we will find for that particular, during that particular time, what will be his range. So after finding the time to complete a vertical displacement of 3 meters, find the horizontal displacement or the range. If that horizontal displacement is greater than 100 meter or equal to 100 meter, he will touch on the other side of the bank. Otherwise, he will fall into water. That's all, right? Nothing harder. So in my video, I told I'll give the link for the 2 videos I did already for the projectile motion. There I did more challenging questions. The questions on a projectile on a bank plane. So it's different questions with harder questions I did it. If you like, you can go through them. So compared to them, these are nothing harder. Only thing I need to find the time to take it to complete a vertical displacement of 3 meters. The idea here, if he wants to land on the other side of the river bank, he need to go vertically downwards 3 meters. That's a vertical displacement. Initially here, finally here means vertical displacement is 3 meters. Or if he wants to fall into water also, the surface of water, the vertical displacement is 3. So after finding the time taken for 3 meter vertical displacement, we will find what will be his horizontal displacement. If it is equal or greater than 100 meter, he will land on the other side of the river bank. Otherwise, he will fall into water. That's nothing. So we'll find the time taken. So vertically downwards, S equal ut plus half at squared for the whole motion. So S is 3 meters, which is downward. Initial velocity vertically, I found it 14.8 meter per second. So that is upward direction. This is towards right. So I am taking downward direction positive. This is upward direction, means minus 14.8 t plus half. Gravitational acceleration is downward. G is 9.81, which is downwards. So I am taking downward positive. So half into 9.81 into t square. Okay, so that is 3 equal minus 14.80 plus half into 9.81 to 4.905. So it's a quadratic equation. Rearrange it. 4.905 t square minus 14.80 minus 3 equals 0. So you know how to solve this quadratic equation by using your calculator in the equation mode. Solve it by using calculator. So you will get the answer. T will be equal to 3.21 second, or T will be equal to minus 0.191 second. We know time is always positive. This is negative. So negative means we take that's not acceptable. So this answer we don't consider. So this is the answer we are going to consider, positive time. So during this time, this is the time taken to have a vertical displacement of 3 meters. So we'll see how much he has gone horizontally during this time. So horizontally use S equal ut plus half at squared. So u horizontally initially we found it 31.7. So 31.7 into time is 3.21 plus half. So horizontally no acceleration, the gravitational acceleration is vertical. It has no horizontal component. Vertical vectors have no horizontal components. Also there is no drag force, so no deceleration. So the horizontal acceleration is 0. Solve it. You will get 101.8 meters, which is greater than 100 meters. So that means his horizontal range is greater than the width of the river. So he will land on the other side of the river bank. So you can give the conclusion. So he will land on the other side of the river bank. Okay, so last part, explain how air resistance would affect the jump. Okay, so what will happen due to air resistance when he's jumping like this from the 3 meters, he's completing a motion like this. So this is the initial height, 3 meters. So when there is drag force, when he is moving up, the deceleration earlier, if there is no drag force, there will be deceleration only due to the gravitational acceleration, which is 9.81 meter per second square. So but here due to the drag force, the deceleration will be more than 9.81 meter per second squared, more than 9.81 meter per second squared. So therefore his maximum height will decrease because he is going to have larger deceleration. So the maximum height he is going to reach is going to decrease. Also, the time taken to reach the highest point will decrease because you can see V equal U plus AT. When you consider vertically upwards, the highest point velocity is 0. Initial velocity vertical component is the same as earlier, initial velocity minus AT. So T is going to be UV over A, UV over A. So where A is greater than 9.81 when there is drag force. So the time taken to reach the highest point will be less. That means he will have shorter time in air. The flight time is going to be smaller. The flight time is going to be smaller means when you consider horizontal displacement, he will be in motion for shorter time with deceleration, because when you consider the time for horizontal displacement, the time is decreasing to reach the highest point. So that means the time is decreasing means he will be in air for shorter time. If he is in air for a shorter time, or he is in projectile motion for a shorter time, but I consider only the half the part of it, so that shows he's going to be in motion for a shorter time. So when you consider the horizontal displacement also, he will be in motion for a shorter time with deceleration. Earlier we considered in the calculation no deceleration because no drag force. But when we consider horizontal displacement, S equal ut plus half at squared. So horizontal initial velocity same as earlier. The time is going to be smaller, and also there will be deceleration. Means you are going to subtract a quantity from UH into T, you are going to subtract a quantity. So the horizontal displacement will decrease. So he might not reach the other side of, or he might not be able to cross the river. He will fall into the water. Okay, so I hope you understood this paper discussion. I'll give the link for both projectile motion, my lessons related to projectile motion, and graphs in the description of this video. Also, I'll discuss other topics and few more past papers related to Unit 1 very soon.